function, we refer to it as a cascade. So when we use that word cascade, it's kind of like a cascading waterfall, right? It's kind of like at the top, you have maybe just one or very few set of proteins that get activated. But just like a cascading waterfall, as you kind of go down, like step by step, right? The waterfall kind of spreads out and you get more and more and more proteins involved. So we're going to draw this out actually on a board, what I mean by the cascade. But what's kind of interesting about these proteins, so even if you just get a few involved initially, eventually by the end, you get all these proteins, they're all recruited and they're all activated, and they're all working together. So eventually they're all stimulated and they all try to attack the microbes, clear it out. All right, the textbook, so this complement system works differently, it has different outcomes. Probably, this is kind of basically a summary of the top 3 functions of the complement system. Basically what ends up happening. So we have 30 different proteins, that's a lot. It's a lot of proteins. And at the end of the day, the outcome of all these different proteins working together is kind of simmered down to these 3 things. Number 1, they'll either work together to just directly kill a bacteria, which is pretty nice. Number 2, what the proteins will do is they'll kind of just get your immune system going even more. So that'll trigger what we call inflammation. And some inflammation is good. Like inflammation is good. It means your immune system is working hard. It's activated. It's responding to something. It's not a pleasant experience to go through when you have inflammation in your body, but that's what it means, that your immune system is responding. The third thing is, what these little proteins do is they actually will make phagocytosis better. So phagocytosis, that cellular eating, works a lot better when there's complement around. So if there's complement around first, then that will actually enhance phagocytosis. Your neutrophils and your macrophages will actually be able to eat foreign material a lot better if that foreign material is coated in complement. So that word opsonization, this is only the 2nd time we've seen it. Opsonization just means to coat, to like coat something. So whenever we see opsonize, it just means coating process. All right, so those are the 3 outcomes. What we're going to do is draw this out on the board. I think I have, oh yeah, here's a picture of the 3 outcomes. So it's showing these, the results of complement. It helps to increase inflammation. So it makes your blood vessels a little bit more permeable, so the white blood cells want to squeeze out and attack the foreign microbes. Also, we know that these little complement proteins will coat. They'll opsonize, they'll coat. So they'll coat the foreign material, like they'll coat the bacteria. Then your white blood cells see that, oh, okay, it's coated, I'll come in and eat it, and phagocytosis. And then the third one we said is a lysing effect. So this is what we're going to draw out on the board. We're going to draw out how that lysing effect, how complement can actually attack bacteria and lyse it. So that's pretty cool because it's basically the same outcome as penicillin. Penicillin works the same way. It attacks the peptidoglycan and our bacteria lyse open. So let's just sketch this out really fast. So what we're going to do is sketch out the lysing effect. We call this the classical complement And one of the things that we have not gotten to yet, but we're going to talk about today, are antibodies. We did say on Monday that B cells of the white blood cell that make antibodies. And we're going to talk about antibodies today. But antibodies are little Y-shaped proteins. So in your textbook, they always show them as like a little Y shape. And that's supposed to be an antibody. And we're actually going to talk about those today. Just to clarify though, antibodies are not a part of the innate, they're actually a part of the adaptive. There. So, but what ends up happening is we're going to talk about these little Y-shaped molecules. They cruise around and they also look for foreign material, and they will also coat, just like complement, they'll also coat the bacteria with themselves as like to flag your immune system that you're sick with something. But what's interesting is, so once these kind of latch on to foreign material in your body, the little stem will actually recruit complement. And the first player in the classical pathway is a little protein that we call C1. And this is supposed to be a protein. So it's made by your liver, it's dumped out into your blood, and C1 is something that floats around in your blood. And what ends up happening is, so the antibody and the complement protein will both kind of link up to each other. What ends up happening is once that interaction takes place, this C1 will go ahead and it'll get activated. And since C1 is the first one, what ends up happening is it triggers our cascade. So it sets in motion now for the rest of the complement proteins to get activated also. So once C1 gets activated, it'll actually work to activate other complement proteins. So that activated C1 will go ahead and recruit other proteins. The two that it recruits, more significantly, are two sets of proteins called C2 and C4. So the only kind of slightly difficult thing about complement is the numbers, they don't go in order necessarily. That's kind of not the very convenient part. You're like, oh, 1, 2, and then 4. But C2 and C4, these are other complement proteins. Complement proteins. Now the other thing is in my picture, it looks like these are getting activated like really, really far away, but in reality, I guess I should kind of emphasize that this whole pathway that we're drawing out on the board, it's actually it would happen like really close to the bacteria. So C1 will get activated, C2 and C4, it would be like really close, like up here. I know it looks like it's far away, but what it would do is it would activate C2 and C4, then these would get activated. Now these are active. And it actually will recruit one big, really important complement protein called C3. And what C3 ends up doing is C3 kind of tends to be the main protein that really triggers the rest of the cascade. C3 will go ahead and it'll activate the rest of our cascade. Activates. The rest of the cascade that C3 will go ahead and pull into the reaction is it'll recruit C5, C6. At least these line C7, C8. So those are all sequential. 5, 6, 7, 8. And then I'll write many C9s. What ends up happening is now finally our cascade is complete. We get all these proteins activated. There's a lot. We have 5, 6, 7, 8. And then all these 9 proteins get pulled in. What ends up happening is all of these tiny little proteins, remember, they're actually really close to the bacteria. They're kind of piled up on top of that antibody. But what they'll do is they'll actually assemble into a donut. Like a donut shape. They'll assemble into a donut shape like a ring, and literally like in a cylinder type shape. So this would actually wrap around in a circle, and this donut shape would actually, this would be made up of the C5, 6, 7, 8, and all the 9s. They would all come together like this ring. And this ring, we call it, this donut shape, we call it MAC. MAC. And that stands for membrane attack complex. So remember on my PowerPoint, we said there were 3 outcomes. One is more inflammation. One is it makes phagocytosis a lot better. And the third one was lysis. This is the lysis effect. MAC, this membrane attack complex. It's basically all of these activated complement proteins. They all form like this donut-like structure. And literally this whole thing will go ahead and it'll poke through the membrane of bacteria. So it'll literally puncture, just like just kind of like a little, what we use for blanking. Punching like a little hole through paper, like a little hole puncher. It's the same effect, only we're doing it through the membrane of bacteria. So that attack complex, once it pierces through the membrane, literally what will end up happening is our original bacteria will lyse and die. So now keep in mind though, what we drew on the board, this membrane attack complex. Membrane attack complex is attacking membrane. So if we had to say like gram-negative versus gram-positives, who do you think would more easily die from that?
Negative.
Would you think it'd be gram-negative or gram-positive? Because they attack membranes. And who has the membrane exposed? That's probably going to get attacked. Yeah, gram-negatives, right? Gram-negatives have the outer membrane. They have an outer membrane that's just sitting there that can get attacked from that. Gram-positives, they don't have an exposed membrane, right? So they just have cell wall built up. So it makes it a little bit more difficult. But at least for gram-negatives, MAC does a pretty good job of attacking membranes. All right, so this is all working to kind of enhance the activity of our white blood cells. So we kind of got complement, we got phagocytosis. Along the way, I didn't say it, but usually these other proteins like C3, they'll also coat bacteria,